So we never actually calculate power in the way that I've described in the previous slides. That's for understanding the concepts, and we assumed we knew sigma and the data were either Gaussian or that the sample mean could be believed to be Gaussian because of the central limit theorem. I think for me personally, the most common function I use for calculating power is this function power.t.test in R. So let's just talk a little bit about t-test power before we talk about how you use power.t.test. The argument is very similar to what we did in our normal distribution case. We're going to reject if our test statistic, in this case x bar minus mu naught over the estimated standard error, is now bigger than a t quantile rather than a z quantile because we're talking about a t-test. Only because we're talking about power, this is going to be calculated not under the hypothesis that mu equal to mu naught, but under the hypothesis that mu equal to mu a, the value under the alternative. It turns out that this statistic, x bar minus mu naught over the standard error, does not follow a t-distribution if the true mean is not mu naught. If it's mu a and mu a is different from mu naught, it doesn't follow a t-distribution. It follows something called the non-central t-distribution, which we're not going to cover. So calculating power requires the ability to evaluate the non-central t-distribution, and that's what power.t.test does for you on your behalf. What's nice about power.t.test is just like before, we have some parameters that we know, mu naught and alpha, and some parameters that we don't know, mu a, sigma, and n, for example. And if you omit one of them but specify the remainder, power.t.test will solve for the one that you've omitted. So let's go through some examples of using power.t.test to either calculate power or calculate sample size or calculate the minimum detectable difference. Okay, let's go through a couple examples, and I'm going to point to this middle one here first. I'm doing power.t.test, so it's calculating t-test power. We're testing h naught, mu equal to mu naught, versus ha, and then the question is whether it's doing a one-sided or two-sided test. Well, in this case, you can see here I've always specified alternate equals one-sided, so that's mu greater than mu naught is what it's testing, or equivalently mu less than mu naught if you appropriately specify the difference in the means as negative. So delta here, this parameter, is the difference in the means. So if I specify n, I specify how different mu a is from mu naught, and I give it a standard deviation of 4. I'm telling it it's a one-sample t-test, and I want one-sided power, and then I'm grabbing the power part of it. Then it gives me my power, 60%. What I show here, you notice in all the other examples I've given here, it also gives 60% as the number. And what I'm showing is that power.t.test, just like the normal power, only depends on the effect size, how different mu naught and mu a are divided by the standard deviation. So here I specify my delta as 0.5 and give it a standard deviation of 1. And notice, so if I'm defining this numerator as delta, notice this is the same effect size as in this case right here. Okay? And since everything's getting a little clouded, let me re-grab my marker. So delta divided by SD is equivalent between that power.t.test call and this power.t.test call, and that's why they give the same number. The same thing is true here, okay, where it's 100 and 200, and if you divide the two, you get 0.5, so it's also true there. Let's go through a couple more examples of using power.t.test. Now, in all of these cases, I calculated power while inputting n, delta, and the standard deviation. Now, let's try to calculate sample size where I give power.t.test the power that I would like. Okay, so now here I'm going to again show you in all three cases that it only depends on the effect size. So here I'm specifying delta of 0.5 and my standard deviation of 1, so an effect size of 0.5 divided by 1, or 0.5, and I'm telling power.t.test I'd like to know what is the relevant sample size if I wanted a power of 80%. Then over here, again, I'm doing one sample and one-sided. I'm grabbing n. Okay? And it gives me a sample size of 26, and then in these kinds of calculations, you always want to err on the side of conservatism, so you bump it up to 27 whenever you get a fractional value. You always get a fractional value, you always want to bump it up to the nearest integer. So you need a sample of size 27 to have a power of 80% to detect an effect size as large as 0.5. And what I'm showing here is that the calculation is the same as I specify an equivalent effect size of 0.5, whether it's delta of 2 over 4 or delta of 100 over 200, it's always giving me the same number. Now what I'll leave as an exercise for you guys is to, for example, omit delta and put in an n and have power.t.test show you what's the minimum detectable delta in order to have 80% power for a specific sample size. And I think given the code that I've given you here, this shouldn't be too hard of a extension. I would say that I almost always use power.t.test as my first attack on a power calculation. One of the main reasons behind this is that power has a lot, as I think I've maybe explained throughout the lecture, power has kind of a lot of knobs and dials that you can turn, and it's very easy to get tripped up on thinking that you have better power than you have, or thinking that you need a smaller sample size. And so when in doubt, try to make your power calculations as simple as possible. So try to revert the question that you're asking down to a t-test or a binomial test or something like that in order to calculate power as simply as possible. And that will give you maybe a slightly conservative either power or sample size estimate, but on the other hand, you'll be able to understand it quite well. From then, you might want to move on to much more complex power calculations, but as a first pass, you always want to do the t-test power or the normal calculation power or the basic power calculation in a binomial problem as the very first thing that you do.